negative force and internal resistance. Before that, let's look at these simple series circuits of an ideal battery connected in series with a resistor. The EMF of the battery is 9 volts and the resistor has a resistance of 10 ohm. Now first, with the switch open, we measure the voltage across the resistor, which is of course 0 volt because there's no current. However, if you measure the voltage or potential difference across the battery, it registers 9 volt. Okay, now let's switch on and the switch is closed. The voltage across the resistor is now 9 volt and the voltage across the battery is also 9 volt. So with those values and the value of the resistor and the voltage across it, you can actually calculate the current, right? So next we will try using real battery. So with open switch, the real battery also register 9 volt between its terminal. And we now close the switch and there is current and the voltage across the resistor is only 8.18 volt. And across the terminal of the battery, real battery, is also 8.18 volt. So this is less than in the case of circuit with ideal battery. So we can actually we can actually measure the current, okay, in this simulation. So let's put a current meter in the circuit and do the experiment again in the ideal battery circuit. So no current because the switch is still open. And the ideal battery voltage is 9 volt. This corresponds to its EMF. We close the switch and measure again the voltage across the resistor. And notice that there is a 0.90 ampere in the circuit. And the voltage across the ideal battery is still 9 volt. So next we look at circuit with real battery. So we switch on the, okay, before that, yeah, it's measured 9 volt. The switch is still open. So we close the switch. Current is now flowing. Measure the voltage across the resistor, 8.18 volt as before. And voltage across the real battery is also 8.18. Notice now the current now is only 0.82 ampere. It is less than compared to the previous case. can you determine what is the internal resistance of the real battery? Now, EMF, amount of energy to drive or to transport 1 coulomb of charge. Example, a battery of 1.5 volt EMF can provide 1.5 joule of energy to transport 1 coulomb of charge. So on the left is the symbol for a real or ideal battery with no internal resistance, where on the right is the symbol of real battery which has internal resistance R. So if we build circuit with real battery, it has internal resistance R, little r, and we switch open, the potential difference between the terminals of the real battery AB is equal to its EMF. So VAB equal EMF. So let's put some numbers there. Let's say the EMF of the battery is 3 volt, internal resistance 0.5 ohm, external resistance is 10 ohm, and the switch is closed, current is flowing. So we can measure the voltage across the resistance and the voltage between the terminals of the battery and also the current. So first calculate the effective resistance. R effective or effective resistance is just the sum of the external resistor and the internal resistance of the battery. Okay, this is equal to 10.5 ohm. Circuit current is the voltage divided by effective resistance. This one turns out to be 0.286 amp, and the voltage across the external resistor VR is 2.86. Voltage across internal resistor of the battery V small r is 0.14 volt. So terminal voltage or potential difference between the terminals of the battery VAB is equal to 2.86 volt. So this VAB is less than the EMF of the battery. So what can we conclude from this observation? Well, when the switch S is open, circuit current is 0. Therefore, the reading of the voltage terminal of the battery is equal to its EMF. When the switch is closed, current flows through internal resistance as well as the external resistance. There will be voltage drop across both internal and external resistance. So therefore, the voltage between terminals of the battery VAB is just the EMF minus the drop in voltage in the internal resistance. Which is why the VAB is less than the EMF